Welcome dear students. So let us begin lecture 6 and continue our study of electrophilic aromatic substitution. In this lecture we are going to study more about the disubstituted benzenes and applications of electrophilic aromatics. But before we go further, let us try to remind ourselves that why we are learning so many reactions, and why is it so important learn so many transformations, remember so many reactions. So as you know that these small organic molecules are very useful because they have very different useful properties. For example, they are used a variety of industries like pharma, chemical, agriculture, textile, food, and whatnot. Let me give you some examples. So this small organic molecule, also known as ibuprofen, is an anti-inflammatory drug manufactured by many pharmaceutical companies and sold as a tablet. Then there are some other small organic compounds like dimethyl sulfoxide and dimethyl formamide, ethyl acetate, and hexane. These are solvents regularly used in laboratories. Then another class of chemical compounds which we popularly know as pesticides are also small organic molecules, and they are used widely in agriculture for crop safety. These are also manufactured by some chemical industry and used in the farms. Then there are other plastics that we come across in our everyday life, like the polyvinyl chloride made from small organic molecules, and also these some other polyester like compounds are made by polymerization reactions, which we some of them we will study in another unit on polymer. Polymers are also derived from small organic molecules and are widely used in textile and other industries. And another small organic molecule popularly known as vanillin is used as a food additive. Many of the foods come in vanilla flavor, so this vanillin compound added. There are many more countless examples of where small organic molecules are used on the commercial scale, either for use as medicine or for materials. But the problem is that only a handful of them are available from natural sources, like Taxol. So Taxol is a very popular anti-cancer compound, but this is not available in quantities large enough so that they can be used by humans for any. Therefore, most of them will have to be synthesized in the organic laboratories by organic chemists like you and me. So let us take one example, that how small organic compounds that are synthesized in the lab by organic chemists can be of use to people. So the most widely used antipyretic and analgesic drug is synthesized from phenol by using a electrophilic aromatic. So in this sequence of steps, first step is that phenol is converted into paranitrophenol by using a modified electrophilic aromatic substitution. In this, ferric nitrite and this ionic liquid is used so that polynitration doesn't take place and the reaction stops at mononitrate. This compound is then reduced in the presence of hydrogen and palladium carbon to give nitrophenol. Paranitrophenol is then reacted with acetic anhydride in the presence of triethylamine, which serves as a base to give you this acetylated para-aminophenol. I leave this as a question for you. Can you identify this drug molecule which is a popular antipyretic and analgesic? And we will discuss more about this in the class. Now let us take some more examples, applications of these activating and deactivating groups in the synthesis of small organic compounds. Here you can see that if you want to make nitrobromobenzene, you could start with benzene, then nitrate it using a mixture of nitric acid and sulfuric acid to get nitrobenzene. And this when you do halogenation, nitro group is a deactivating group. You will direct the bromination at the meta position and you will get only one bromo 3 nitrobenzene. So if you wanted to make the para substituted compounds, this sequence won't work. A slight modification can give you the benefit and you can synthesize ortho and paranitro compounds by taking the advantage of the activating and deactivating abilities of the substance. So in this second modification, benzene is first halogenated using bromine and ferric tribromide. This introduces a bromine atom in the benzene ring to give you bromobenzene. When you nitrate this compound, because the halogens are orthopara directing but slightly deactivating, they will direct the nitration at the ortho and para position, and therefore you will get good to moderate yields of the ortho and para compound, which is not possible using this sequence. So further we can see that there are more applications of electrophilic aromatic substitution, and these reactions can easily be used to synthesize a wide variety of compounds. Well, let us take these nitrobenzoic acid. So suppose you wanted to make all of them from toluene, then how you would like to proceed? First you want to oxidize the toluene to the benzoic acid using the oxidizing agent KMnO4, potassium permanganate. But once this methyl group is converted into carboxylic acid, we know that the carbonyl groups are meta-directing and deactivating. Therefore, under nitration conditions, most of the time only mononitration will take place to give you meta-nitrobenzoic acid. Therefore, this sequence will give you meta-substituted compound, and if you wanted to make the ortho or the para-substituted compound using the activating properties of the methyl group, first we will do nitration. So this nitration will give us the orthonitrotoluene and para-nitrotoluene, which we could isolate by doing chromatographic separation, and then these can be further oxidized to give you the orthonitrobenzoic acid and para-nitrobenzoic acid. So here this is another example of a use of the activating and deactivating abilities of different functional groups, but there are many endless examples available in the literature, and more examples we will study in the class. So let us pay more attention towards the mechanism of this electrophilic aromatic substitution reactions and what do we know about them. So we have studied from the last lecture, we know that because of the substitution pattern, rates of these reactions are not same. Some are faster, some are slower, and also the substitution affects the orientation, that is whether you get the ortho or the meta substituted product. So what are the mechanistic reasons that we see this pattern? Also, we would like to know more details about the mechanism. But one thing is clear and almost obvious, that although most of the electrophilic aromatics have a common mechanism, the way or the reactions which are used to produce the electrophile may not be similar, and in fact in many cases they are quite different. So let us take this example of nitration. In nitration, we know that once the electrophilic nitronium ion is generated, it is attacked by the electrons from the ring to get this positively charged intermediate, which then proton is lost to get the nitrobenzene. But how do we get the nitronium ion in the first place? Because we know that nitric acid is HNO3, and it tends to dissociate this way, giving you a proton and the nitrate ion. Therefore, how you would get the NO2? That means we have to force the nitric acid to dissociate the nitrogen oxygen bond instead of the usual oxygen hydrogen bond. For this we need a strong acid like sulfuric acid. Once you add sulfuric acid to nitric acid, the reaction between the stronger sulfuric acid and the weaker nitric acid takes place. In this, stronger sulfuric acid donates a proton to the oxygen, forming this species which easily loses a molecule of water to give you the nitronium ion. Pay attention to the fact that nitric acid here is behaving like a base. The reason for this is the presence of the stronger acid, sulfuric acid, is forcing the nitric acid to act like a base. Then with this information we can move forward to study further the mechanism of nitration of phenol. So once we know how nitronium species is generated from nitric acid and sulfuric acid, we can study the mechanism of nitration of phenol in a bit detail. So here you can see phenol electrons from the ortho position of the phenol ring attack the nitronium ion. You will see that three intermediates with positive charge will be formed. In this, the first one is very stable because the positive charge gets delocalized on the oxygen atom, and which can share its lone pair of electrons with the ring, thus giving a very stable structure. In the other two structures, such sharing is not possible, but therefore the contribution from this resonance structure is very high, and once that this intermediate is formed, it quickly loses the proton to give us the nitrated phenol. So electrons from the ring add to the nitronium ion. This leads to the formation of the positively charged intermediate, which is stabilized by delocalization, and you will find that similar structures are possible for the attack of the ring from the para position to the nitronium ion, and a very stable intermediate structure because of the resonance by the oxygen lone pair is possible. So very stable structures are possible where oxygen carries partial positive charge, but such structures are possible only for the ortho and para attack. Now let us see what structures are possible when there is a meta carbon attacks on the nitronium ion. In this case, three resonance structures are possible. In none of them, the oxygen is able to delocalize. For no extra stability is available to this inter. Therefore, it is clear that nitration of phenol is electrophilic aromatic substitution, which involves two steps. So let us, you will find that similar structures for the intermediates can be formed for attack of electrophiles at various aromatic rings like toluene, nitrobenzene, or halobenzenes, or even carbonyl substituted benzene rings. I leave it for you to pay attention to these resonance structures. So it is highly recommended that you draw and redraw these structures and try to understand which of them are inductively stabilized, which of them are unstable, and for what reason. We will spend some time doing extra practice on these structures in the classroom. This will also help you for preparing in the exam. So therefore, it is clear that electrophilic aromatic substitution is a two-step reaction in which the first step is the attack of the benzene ring on the nitronium ion, and this is the slow step, and the second step involves a very rapid loss of proton to give the product. Now, as we have seen potential energy surfaces in the last semester, this electrophilic aromatic substitution involves transition states for each step. That means once the electrophile and the aromatic ring come close together, initially there is a repulsion between the ring and the electrophile. This could be because of the steric repulsion. Therefore, the energy of the system rises, but it rises only to certain extent. Once the electrophile and the carbon atom of the ring are close enough, they start to form bond, and the formation of this bond releases energy, and the energy of the system comes down. You will find that the first step requires large amount of energy, whereas the second step, that is the breaking of the carbon hydrogen bond, requires only a considerably small amount of energy to get initiated. Therefore, it is the step 1 that is the rate determining or slow step, and step 2, which is the carbon hydrogen bond dissociation, is very fast and doesn't have any effect on the rate or orientation of the reaction. One may ask, what is the evidence for this two-step mechanism? So that means that let us try to propose a new mechanism in which we say that the electrophile attaches to the ring and the hydrogen leave in the same step. That is, if the reaction involves a single transition state which includes the removal of hydrogen. Suppose this uh, removal of hydrogen was a crucial step which was part of the rate determining step, then the rate of the reaction will be slowed if hydrogen is substituted by a heavy deuterium, and thus we should see hydrogen isotope effect. This hydrogen isotope effect you have also seen in the last semester. But what is the fact? The fact is that we don't see any hydrogen isotope effect in the electrophilic aromatic substitution. That means the CH bond is not broken in the rate determining step. This is not a single step reaction. That means it is a two-step reaction. So therefore, instead the CH bond breaks in the second step, that is very fast. And because it is very fast, it doesn't matter whether it is the CH bond that is breaking or it is the CD bond that is breaking. So nitration and essentially most of the other electrophilic aromatic substitutions are a two-step process which involve a positively charged carbon atom or carbocation. So let us move towards and try to uh, understand the mechanism of other electrophilic aromatic substitution reaction. So in the case of sulfonation, you will find that two molecules of sulfuric acid, one acts as an acid and the other acts as a base. So this one, it donates its proton to the other one, generating OH2 plus, and there, because water is a good leaving group, it leaving behind SO3H species, which quickly loses another proton to give the sulfur trioxide. Now sulfur trioxide is an electrophilic species, and which is formed as a result of the acid base equilibrium within the H2SO4. Now in the second step, this sulfur trioxide, which is the electrophile, is attacked by the benzene ring to give the intermediate carbocation, and then in the third step you will find that the carbocation quickly loses the proton to form the ionized benzene sulfonic acid. Now this ionized benzene sulfonic acid is very weak acid than the sulfuric acid. Benzene sulfonic acid is a weaker acid than the sulfuric acid. Therefore, it accepts a proton from the medium to give us the benzene sulfonic acid. So you will find one thing you will find unique here is that all these reactions are for all these reactions reversible arrows are written. This suggests that these are reversible reactions. Now let us try to understand the mechanism of the Friedel-Crafts alkylation. Here the first step is slightly different because the electrophile that is generated is R plus. First of all, the alkyl halide is reacted with aluminium trichloride. This results into a ion pair formation in which R plus is formed transiently. This R plus, because it has electrophilic properties, is attacked by the aromatic ring to give the similar intermediate species where carbocation is delocalized between the ring carbon atoms, and this intermediate then quickly loses a proton which is accepted by the tetrachloroaluminum species to give us the alkylated benzene, and we get the aluminium trichloride back along with HCl in the reaction medium. So one thing you will notice that this reaction gives us an opportunity to form new carbon-carbon bonds, and that is why this is a highly important reaction. Based on this discussion and the earlier ones, I leave a task for you, that is to formulate a short description for this reaction based on what we have discussed here. A very similar reaction is a Friedel-Crafts acylation. In this, instead of the alkyl chloride, acyl chloride, that is RCOCl, is treated with the aluminium trichloride to get the acylating agent RCO. This RCO, being an electrophilic species, is attacked by the benzene ring to give a similar carbocation which is resonance stabilized by these structures, and then the intermediate immediately loses a proton to give the acylated benzene derivative and the aluminium trichloride and HCl. Similarly, we can see halogenation of the benzene ring can be performed using halogens and ferric trichloride. This reversibly will form this complex in which one of the chlorine atom is having a electrophilic character. This is because it is electrophilic, it is attacked by the benzene ring depicted here as C6H6, and this leads to the formation of the carbocation intermediate where the positive charge is delocalized within the benzene, and this is the slow red determining step. After that, the intermediate quickly loses a proton to give the chlorinated benzene, and this is a fast step. Now, would you like to answer this question that in chlorination reactions of some activated benzene derivatives, hypochlorous acid is used along with HCl as a catalyst? Can you explain the role of H plus in this? So here are some of the questions that you may want to solve from Morrison Boyd textbook from chapter 15 of the 6th edition. Questions 1 to 10, which are given at the end of the chapter, will help you revise more about the electrophilic aromatics. So see you in the next class. Thank you.